Okay, in this video I'm going to show you how do we draw the vector diagram of a loaded alternator. At first I will show you the vector diagram of alternator when it is loaded with lagging, leading and unity power factor load, and second one is that I will derive the equation of no load voltage EPH for each of the case. Okay, let me start. This is the per phase equivalent circuit of an alternator. If we load the alternator with a load impedance ZL, we have three other parameters to be considered: armature resistance drop IARA, armature leakage reactance drop IAXL, and armature reaction drop IAXR. And you know that our leakage reactance and reactance due to armature reaction is combined to get our synchronous reactance XS. So therefore we will consider only two parameters: armature resistance drop and armature synchronous reactance drop. Okay, now so if I apply Kirchhoff's voltage law in this equation, if I apply Kirchhoff's voltage law in this closed circuit, see here we are generating a voltage EPH. This EPH is our no load voltage. Some portion of this EPH is dropped in this resistor, in the synchronous reactance, and the rest of them are dropped in this load. So if I apply Kirchhoff's voltage law here, Phasor form, I can write EPH with vector sign equal to VPH plus IARA plus IAXS, and on top of that I have to give the Phasor sign. This is our generated voltage and these three are the voltage absorbing element. Kirchhoff's voltage law equal to summation of voltage rise or voltage supplied equal to sum of voltage drop in the circuit. Okay, so if I want to draw the vector diagram of loaded alternator, I have to satisfy this equation such that our Phasor no load Phasor voltage will be equal to the sum of full load or load voltage VPH plus armature resistance drop IRA plus IAXS. See, if you are familiar with the addition of a vector, let's say we have a vector A1 here, and this is the initial point of A and this is the final or terminating point of A1. Let's say I have drawn another vector A2 here. Its initial point is here and its final point is here. Let's say I have drawn another vector A3 here, and see, A3 has started its journey from this point, the final or terminating point of A2, and it ends at, let's say, this point. Now if I want to get the resultant of these A1, A2 and A3, I have to join the beginning of A1 and the terminating point of A3, which I can do like this. If I join these two points, let's say the vector I get is our A vector and its direction will be in this direction. Now say I can write A vector equal to A1 plus A2 plus A3 vector. Okay, and see, this A vector will indicate the resultant of all these vectors. So if I want to draw EPH will be the sum of VPH plus IRA and the IAXS. So this VPH will be our A1. We have to start IARA at the terminating point of this A2, and we will start the IAXS drop in the terminating point of A2. If I add all these three, I will get our EPH. I am discussing the prerequisites, the basic knowledge you have to know to draw the vector diagram of a loaded alternator. Okay, now I will discuss what are the steps we have to follow to draw a vector diagram of a loaded alternator. Whenever we draw a vector diagram, at first we have to take a reference phasor, and we take the reference phasor in that parameter which remains same throughout that circuit. Now see, in this circuit. This is a series circuit, and throughout the circuit our armature current IA will remain same. Therefore I will take the IA as our reference phasor, and its direction and value will be constant in every case. Okay, now second one is that after taking the phasor, reference phasor, we have to draw the VPH. Now see, VPH is the voltage drop across the load. This load could be a resistor, a pure inductor, pure capacitor, a combination of resistor inductor, combination of resistor capacitor, or resistor inductor and capacitor, or inductor capacitor, whatever. Depending on the type of the impedance, I will get the phasor of VPH. Now see, there could be 4 or 5 cases. If I use the resistor as our load impedance, we will get IA and VPH in same direction. You know that this relation. If we take the phasor in a resistor, the voltage drop in it and the current through it goes in the same direction. Therefore the angle between them will be 0. Therefore our power factor cos phi will be equal to 1. Therefore as the power factor is 1, this type of load is known as unity power factor load. If our load is a pure inductor, that means in a pure inductor, what is the relation of voltage and current? If we take the voltage in this direction, current will be 90 degree lagging from this voltage, as we have to take the VPH. If VPH goes in this direction, and I will get the VPH due to the current flow IA through this load impedance. Therefore our IA will be 90 degree lagging from this VPH if we use a pure capacitor here. And see, as the current is lagging here, our cos phi will be equal to 0, and this type of load is known as lagging power factor load. If I use a pure capacitor as our load, you know that if we take a capacitor, if voltage goes in this direction, and our current will be 90 degree ahead or leading from this voltage in the capacitor. Therefore the voltage VPH will be dropped in the capacitor due to the flow of current. Therefore I will take, if I take the VPH in this direction, our IA will be in this direction, and IA will be 90 degree leading from this VPH due to this capacitor. Now if see, as the current is leading here, therefore our load will be known as leading power factor load. Okay, if I use the series combination of a resistor and inductor, in case of series, voltage and current goes in the same direction. In case of an inductor, voltage and current goes in 90 degree lagging direction from this voltage. If I take the combination of resistor and inductor, our current will be lagging this VPH by an angle of phi, and the value of this phi will be less than 90 degree, but it will be greater than 0 degree. As the current is lagging here, therefore this type of load is also known as lagging power factor load. If I use the series combination of resistor and capacitor, in the resistor voltage and current goes in the same direction, and in the capacitor current leads V by an angle 90 degree. Therefore our current IA will be leading this VPH by an angle, but that angle will be greater than 0 degree but less than 90 degree. Therefore our cos phi will be less than 1 but greater than 0. As the current is leading here, this type of load is known as leading power factor load. Now we are done with our VPH. According to the type of load, I will draw the VPH. After drawing VPH, from the terminating point of VPH, I will start drawing our IARA drop. See, IARA, this voltage drop is a resistive drop. Therefore its direction will be in the same direction of IA, and we have to start our drawing from the end point of VPH. Let's say we are done with our drawing of IA RA in the direction of IA. Therefore, from the end point of IRA, I will start drawing our IA axis drop. See, IA axis is an inductive reactance drop. In an inductor, we know that if the voltage is going in this direction, current will be 90° lagging. See here, IA axis is the voltage drop. If I take IA axis in this direction, and this IA axis drop is due to the current of IA, therefore IA will be 90° lagging from the IA axis drop. Now see, if I complete our drawing IA axis, therefore the beginning of VPH to the addition of the end point of IA axis will be our resultant phasor EPH. Now I will show you how do we implement this algorithm or these steps in drawing the vector diagram of alternator with different types of load. Okay, now I will show you how to draw the vector diagram of an alternator when it is loaded with a unity power factor load. Unity power factor load, that means I will use a pure resistor. Okay, pure resistor as this load impedance. I will use a resistor. So if I apply Kirchhoff's voltage law in this per phase equivalent circuit, I will get supplied voltage EPH equal to VPH plus IARA plus IAXS, and you know that this IARA drop and this IAXS drop will be equal to the voltage drop equal to our synchronous impedance. Therefore I can further simplify this equation, VPH equal to plus IAZS, and on top of that a vector sign. So I can write EPH equal to VPH plus IAZS. Now I will draw the vector diagram, and after that I will show you the relationship between this EPH or no load voltage EPH and the full load voltage VPH here. Okay, at first we have to take the reference phasor IA. See here, from this point I take the reference phasor IA in this direction, which I have indicated with this black color, and this is our IA, armature current IA. Okay, this is, and I am taking this IA as our reference. After that we have to draw the VPH. See, VPH is the voltage drop across this resistor R when this R is used as load due to the current flow IA. Therefore the voltage drop VPH will be equal to IA into R. So VPH will be in the same direction as this is a resistive voltage drop. If I take the IA in this direction, our VPH will be in this direction, which I have indicated with this green color. Okay, this is the terminating point of the VPH. After drawing VPH, I will take the voltage drop IA RA. See, IRA is a voltage drop due to the current flow IA through this resistor, as this is also a resistive drop, so I will take IRA in the same direction as IA here. Okay, which I have indicated with this red color. See, after that this is the terminating or in final point of our IARA. After that I will take another drop IAXS drop due to the current flow. This is our voltage across this synchronous reactance VLXS equal to IAXS due to the current flow IA, as I am taking the direction of current in this direction. See, as this is an inductive drop, in an inductor the voltage will be 90° leading from the current. Therefore if I take the IA in this direction, our voltage drop IAXS will be 90° from the direction of this IA. Therefore I will draw the IAXS in this direction, 90° leading with respect to this IA. So now if I add this point and this point, which I have indicated with this violet color, I will get our desired EPH. Now see, this IARA and this IAXS drop indicates the voltage drop between this point to this point, so I can write it with IAZS. Okay, so this is the vector diagram of unity power factor load. After that I will establish the relationship between this EPH and this VPH. See here, our AB, this AB equal to our full load voltage VPH, BC equal to IRA, and CD equal to our IAXS. And another thing, this, see, this AD equal to EPH, and this BD indicates our IAZS drop. Okay, now consider this ACD. This is a right angle triangle, so I have to take the Pythagorean. This is the hypotenuse, AD square. So this AD, this hypotenuse square, will be equal to AC square plus CD square. Okay, so I can write AD square equal to AC square, this AC square, this is our length 1 and this is our length 2, CD square. See here, AC equal to AB plus BC. I can write AC equal to AB plus BC whole square plus CD square. Now see here, AB equal to VPH and BC equal to IARA, and this CD equal to IAXS, from which I can write, and see this AD is our EPH. So if I put the value of our required parameters, I will get EPH square equal to VPH plus IARA whole square plus IAXS whole square, which implies that our no load voltage EPH will be equal to root over VPH plus IRA whole square plus IAXS whole square. Okay, so when we load an alternator with resistive or unity power factor load, our EPH will be equal to root over VPH plus IRA whole square plus IAXS whole square. Okay, that's it. Thank you.